Okay, so then welcome everybody to today's ACPMS seminar. It's my great pleasure to introduce today's speaker, Philippe Bianne, who's the research director at the CNRS in Paris. And he's going to talk about combinatorics of the quantum symmetric simple exclusion process, Schroeder trees, and free cumulants. And we're very much looking forward to your talk.
Okay, so thank you very much for the invitation and for the presentation. So this talk will be about some combinatorics, which is inspired by physics, directly inspired by physics. In fact, I was contacted by a physicist in Paris, Denis Bernard, a few months ago. He had some very nice polynomials and he wanted to find a combinatorial formula for them. And so I did some work and finally I came up with a formula. And this formula turned out to be, I was very surprised by that. The formula turned out to be a formula involving free cumulants. Actually, these polynomials are, in some sense, free cumulants, and it is quite surprising. So I will show you why. So my main topic will be these loop polynomials. These are a family of polynomials, which are indexed by circular permutations of 1n. So they depend on n variables, x1, xn. So let me show you a few of them. So the first one with one variable is just x1. When I have two variables, so there is only one circular permutation, which is permutation 1, 2. And it's x1 times 1 minus x2. When we have three variables, it's x1 times 1 minus 2x2 times 1 minus x3, and it's the same for the two circular permutations. And when we have four variables, so there are six circular permutations, and this time there are two different polynomials. One of them is q1, 2, 3, 4, so the cycle 1, 2, 3, 4, and it's given by the formula you can see. And there is a slightly different formula for the cycle 1, 3, 2, 4. And four of them are equal to the first formula, and two of them are equal to the second. And as you can see from the formulas, it seems that there is a combinatorial flavor to these polynomials because we have integers with some signs that you can predict, and as coefficients of the polynomials. And okay, and there is of course much more structure, and we will see what is this structure which is behind these polynomials. And this structure was noticed by the physicists who came up with these polynomials. Okay, so where do they come from? Well, they come from asymptotic fluctuations of something which is called the quantum symmetric simple exclusion process, which is something which I'm going to explain. I will not go too much into the physics because it's not my field, and also because it's I think it's a very interesting, there are many interesting things to say about that, but I will rather stick to the combinatorial side of the things. But I will give the motivation for looking at these polynomials and where they come from. So my goal will be to give the combinatorial formula which is behind these formulas, and explain also that these formulas that you get to see here are in fact free cumulants. Free cumulants of variables which are not free, because if they were free, they would be essentially the cumulants would be zero. But they are free cumulants of a family of very simple family of random variables, which are in fact commuting projections. And we will see what they are in fact. So first, I will explain the motivation and where these polynomials come from. They come from the study of the quantum exclusion process, but first I will recall what is the exclusion process. So the exclusion process describes particles which are hopping on an interval and which satisfy the exclusion principle. So there are n sites which form an interval, and there is at most one particle per site. So here is, for example, is a configuration. So let me explain. So you have n sites. Each site is either occupied, which I denote by a black dot, or it is unoccupied, where you have a white circle. So the particles, of course, are on the occupied sites. And at some point, they decide whether they want to move either to the left or to the right, to the next neighbor, either to the left or to the right, with some probability, P or 1 minus P. In our case, we will stick to the case where it is symmetric, that is P is equal to 1/2. But there is the exclusion principle, which tells you that there is at most one particle per site. So if the particle that is here decides to go to the right, well, if the site is not occupied, it can go to the right. So it will just jump to the next thing, to the next site. But here, if it wants to go to the left side, which is occupied, then it cannot. So nothing happens. And so this is the dynamics for this process. And you have to add some things which happen at the boundaries. So this interval is in contact with some reservoir where there are many particles. And some particles are coming from the left with some rate which is alpha, or they are going out from the left with some rate which is beta. And the same thing happens on the right, independently, of course. Some particles may, if a particle is present on the right, the last site n, it can go to the right with some rate gamma, or if the site is empty, it can some particle may come in with rate delta. Okay, so this is the dynamic of the exclusion process. It's a very well-known stochastic process, and it has led to many papers. Now it's very popular. There are many connections, especially connection with random matrices or non-permutations, and okay, a lot of combinatorics is behind this process. So one of the things you can look at is what happens in the large time limit when there is a current which is established, that is particle in the mean behavior of particles is that they go either to the right or to the left, depending on the rate of the entrance or exit at the boundary points. And the configuration of particles converge to a stationary measure, which is a probability measure on the set of all configurations. So the set of all configurations is just 0, 1 to the n, where 0 is just the site with empty site. If at some site you have 0, it means the site is empty, and 1 if the site is full with one particle. Okay, so now let me describe the quantum symmetric simple exclusion process. So it's a quantum version of the preceding process. So this means that instead of having a stochastic process, we have a certain Hamiltonian, which is this Hamiltonian, which I'm writing here. I will explain what it means. So it is a self-adjoint operator, HC. So this HT depends on where first there is some Brownian motion, there is some noise. So that's the dynamic is stochastic. There is some noise which is a complex Brownian motion, independent complex Brownian motions. And there are some operators which are just classical quantum, fermionic creation and annihilation operators. So they satisfy this anti-commutation relation, the canonical anti-commutation relations, and they act on some space V, which is the quantum version of the classical state space. So it's just, if you want, the L2 space of the space omega, which is here. So a state in V is just a vector of norm 1. And among these states, there are some classical states, which are the states of the form of tensor product, EI1, tensor, etc., tensor EIN, where EI has just the basic canonical basis of C2, where E0 represents the empty state and E1 the occupied state. So we have a Hamiltonian, which is so it's a random matrix of size 2 to the n, acting on the space V, which is so evolving according to some Brownian motion. And now the distribution of the quantum particles, it is determined by a density matrix, which is a positive Hermitian operator on the space V, whose trace is equal to 1. So it satisfies some evolution equation, which is written in this way. It's a stochastic equation of there is some so see ht is a Brownian motion, and so when you see the product of dht, it means that we are using the Ito formula. I will not insist on this because it's I'm not really interested in explaining in detail the physics. I just want to motivate the introduction of the to explain where these polynomials come from. Okay, and there is some boundary term which describes what happens at the boundary sites, which I will not detail. But it's exactly the analog of the stochastic process, which is a classical exclusion process. It's a quantum version. So what we can see about ρt, it's a random matrix. So if the initial configuration is a diagonal on the classical state, so it's a matrix acting on the space V. If it is diagonal on the basis of classical states, then its expected value will remain diagonal on these classical states, and it satisfies the same evolution as the classical symmetric simple exclusion process. So this is a quantum version, but in some sense you can get also the classical version by taking the expectation with respect to the noise, and it satisfies in some sense the same evolution. Okay, so now when times goes to infinity, we know that the ρt, this matrix will converge in distribution towards a stationary state, which is a random matrix of size 2 to the n. So it's a very large matrix. It has size 2 to the n. But the physicists are interested in something which is a little bit smaller, which is the two-point function, GIG, which is just the trace of the matrix ρ evaluated on the multiplied by the CI, so the annihilation operator at site I, and the creation operator at site J. So these two-point functions, they measure the correlation between the sites A and J, and they form a random matrix J, which is of size n instead of 2 to the n. So it's a smaller matrix. And it is really these random variables which are interesting. So it's a random matrix of size n. When n goes to infinity, it will become, of course, a large matrix. And what we are interested in is the fluctuation of these matrices. So these fluctuations, they will be measured by the cumulants. The physicists call this the connected correlation functions, but we have a family of random variables. So we may want to measure compute their cumulants. So on the left of the equation, which is here, I have just put the physicist notation for, they say this is a connected correlation function. On the right, it's more mathematical notation. We call this the cumulants, classical cumulants. And these are the quantities that interest the physicists. They want to measure the fluctuation of these variables and to see that they encode in some sense how the correlations between the sites fluctuate when and we will be interested in the asymptotic of these correlations. So what physicists know is that when n goes to infinity, the leading cumulants scale as n to the minus p plus 1, where p is the number of variables that you look at. So here you see I have taken a cumulant of p variables. So when n goes to infinity, the leading cumulant, they have a scale like n to the minus p plus 1. And what we can say is that only some of them have non-zero limit. Only the one for which the G1, GP form a cyclic permutation of I1, IP. Only this one of the non-zero limit. So we can describe this limit by saying that if we look at the sites I1, IP, and we divide them by n, so we obtain numbers which are between 0 and 1, real numbers. rational numbers in this case, but we assume that they converge to some real numbers, some locations on the interval 0, 1. And when n goes to infinity, then these cumulant will converge. So this cumulant, which corresponds to some cyclic permutation of I1 IP, the cyclic permutation I1 IP, they will converge to some, or they will scale like some function GP of U1 UP, plus some term which goes to 0 as n goes to infinity. So these functions are the functions which are the things that interest the physicist, which measures the fluctuations of these correlation functions. Okay, so this GP, it turns out that they are piecewise polynomial functions. And they are polynomial in each sector, which corresponds to a certain ordering of the UI. You see that the UI are numbers between 0 and 1. They can be ordered as you like. Here we are looking at them as forming a certain cycle. There is a certain cyclic permutation of these numbers, but these numbers could have any order on the interval 0, 1. So in order to understand this function, what we will do is just look at this function as polynomial in each sector, which corresponds to an ordering of the UI. So this brings me to the main topic of this talk, the loop polynomials, which were introduced by Bernard and Jean in a recent paper in 2021. These polynomials are defined in the following way. They correspond to taking, they are indexed by circular permutation, sigma. Their variables are numbers x1, xp, which are ordered, totally ordered in this way, between 0 and 1. So x1 is smaller than x2, smaller than x3, smaller than xp. And they are indexed by a circular permutation, sigma, so that the connected correlation function, or if you want the cumulant of this random variable, so j I1 I sigma to the p minus 1 of 1, I sigma to the p minus 1 of 1, I sigma p minus 1 of p minus 2 of 1, etc. This will converge to this q sigma evaluated at x1 xp. And here we assume that just that ik over n converges to xk as n goes to infinity. So if you want, the q sigma, they are just the functions which I call g in my previous slide, but they correspond, I look at them as on the totally ordered set, x1, xp, and I index them by some permutation sigma. So they correspond to the restriction of the function g that I had before to all the possibilities of ordering the numbers x1, xp, or u1, ups, as I call them in my previous slide. So the q sigma are the loop polynomials. So they give the values, as I said, of the function gp in each sector corresponding to some ordering. So now they are really the interesting objects, and I'm going to describe them now as I will now give an algebraic characterization as what was obtained by Bernard and Jean in their paper. So this characterization is the following. It's a simple algebraic characterization. So the q sigma, first they are of degree 1 in each of the variable xa. So this is the first property that they have. For the small value of small number of variables, they are given by just q1 of x1 is x1, and q12 of x1, x2 is x1 times 1 minus x2. They satisfy some boundary conditions. That is, you remember that x1 is the smallest of the variable. So it's the q sigma is always factorized as x1 times some polynomial of the variables x2, xn minus 1 times 1 minus xn. So you see that it vanishes at x1 is equals 0 and at xn equal 1. Remember that xn is the largest of the variables and x1 is the smallest. So this means that the fluctuation, that in some sense, at the boundaries, the fluctuations are very small because they vanish when x1 is 0 and when xn is equal to 1. So when one of the points, either x1 or xn approaches the boundaries, the fluctuation reduces. Okay. Now they satisfy a continuity condition. So this continuity, you see what happens when you try to exchange the order of xi and xi plus 1. So you look at the boundary between two of the regions. So when xi is equal to xi plus 1, and then you see that q sigma is equal to q, where I and I plus 1 are exchanged when I look at the boundary of the region where xi is equal to xi plus 1. So this is one of the boundaries between these regions where xi is equal to xi plus 1. And you see that at this boundary, the q sigma coincides. So this means just that my function g that I had before are continuous everywhere. So it's a very natural condition. And now there is a slightly more complex condition, which is really the conditions that encodes all the combinatorics of these objects. It is the following one. There is some exchange relations. It tells you what happens when you go from one region to a neighboring region. Again, this corresponds to conjugating the cycle sigma by the transposition Si. So sorry, I didn't explain what is Si. Si is just the transposition of I and I plus 1. So Si sigma Si is just the transposition with exchanges I and I plus 1 in the circular permutation. Okay, so this exchange relation tells you that the coefficient of Xi between the difference of the coefficient of Xi between Q sigma and its permuted version, where I and I plus 1 are exchanged, and plus the coefficient of xi plus 1, again, of this difference of the two polynomials between the two regions. This is equal to something which is here, which is, I will explain in a minute what it means, but here we have the coefficient xi, which is of the polynomial q sigma 1, q sigma minus of x minus times the coefficient of xi plus 1 in the polynomial q sigma plus of x plus. So here, what are sigma minus and sigma plus? Well, you multiply on the left sigma by some transposition Si, and then it can be written as a product of two cycles. One of the cycles contains I plus 1, and this other cycle contains I. And I call these cycles sigma plus and sigma 1. So I explain what it means. So here, I show you a picture of the circular permutation sigma. You see somewhere you have I and somewhere you have I plus 1 on the cycle. When I multiply on the left by the transposition Si, which exchanges I and I plus 1, what I get is that this cycle is split into two cycles, sigma plus below, which contains I plus 1, and sigma minus above, which contains I. And now, if I multiply on this permutation on the right by Si, what I get is just the original cycle, but where I have just changed the position of I and I plus 1. Okay, so you see here I have sigma 1, sigma plus, and so when I go back on my formula here, I have a certain circular permutation, sigma 1, and a certain number of variables, x minus. So x minus as the variables which are permuted by the cycle sigma 1. Okay, so if you want, there are the variables that you see in this cycle here. sigma 1, which is here. And the same for sigma plus here. The variable x plus are the one which appear on this cycle. Okay. So let me just show you how to use these defining relations. So suppose you know your polynomial q sigma, and you know that you can expand q sigma into the form a plus xi b plus xi plus 1c plus xi plus 1d, where a, b, c, and d do not depend on the variable I and I plus 1. They just depend on all the other variables. So this is just because, as I said, q sigma is of degree 1 in each variable. So only this term in xi and xi plus 1 can occur in your polynomial q sigma. Now let me do the same thing for the pure polynomial q si sigma si, where I have just exchanged the variable I and I plus 1. So now there is I prime plus xi b prime plus xi plus 1 c prime plus xi plus 1 d prime. Okay. Now remember I had a continuity condition which says that the function is continuous in some sense. So this means that this function, when I am at the boundary between the region corresponding to sigma and si sigma si, which correspond to xi equal xi plus 1. On this boundary, the two polynomials should be equal. This means that a should be equal to a prime, d should be equal to d prime. And here, when xi is equal to xi plus 1, the sum of the two polynomials should be equal. So b plus c should be equal to b prime plus c prime. Okay? So when I go from one region to the other, what changes in my polynomial is just the coefficient b and c, they change, but they sum remain the same. And now the way that they change is encoded into this polynomial delta, which is the coefficient of xi in this polynomial q sigma minus, sorry, and this polynomial q sigma plus of x plus. And now the exchange condition tell me essentially that b minus sigma c prime is equal to c minus b prime, and this is equal to delta, this polynomial here. So this exchange condition tells me how the polynomial changes when I change the ordering in the variable between the variable I and I plus 1. Okay, and so this means that if you know q sigma for one cycle, then you know q sigma for all n cycles by using all these relations. You can go from sigma to si, sigma, si. And of course, by doing such conjugation, you can go from one cycle to all the other cycles that you want. So you just need to know it for one cycle. Okay. And now what Bernard and Jean proved is that this condition above completely determine these loop polynomials. They are completely determined by this condition, essentially because you have the boundary condition. The boundary condition, they put some very strong requirement on this polynomial. Because if you know that q sigma, for example, satisfies the boundary condition, and you apply this change using this algorithm here, it's not obvious that the new polynomial will satisfy the boundary condition. So having all these boundary conditions, the continuity correlation and the exchange relation, this completely determines the loop polynomials completely. Okay, so now let me give some new examples, a little bit more complicated. For n equals 5, so for n equals 5, you can apply these algorithms and check that you have these formulas. Now we have 4 different polynomials. They are given by these formulas that you can see here. And many of them are equal. You can see there are essentially 8 of them are equal to the first, 4 of them are equal to the second, 4 of them to the third, and 8 of them to the fifth. And you see that, well, if you go from, for example, from this one to this one, what you have done is you have exchanged 3, 2, and you can see that the coefficient of x2 and of x3 have changed, but not the coefficient of x4. And the coefficient of x2, x3 has not changed. But of course, the coefficient here of x2, x4 and of x3, x4, they have changed. And the sum has not changed. You have 7 plus 5 is equal to 12, and 10 plus 2 is equal to 12 here. Okay, and okay, so of course you can use the algorithm that I described above to compute these polynomials. Okay. So now my goal is now to give an explicit combinatorial formula for this Q sigma, and in particular to explain that they are these polynomials are free cumulants. Which is a bit surprising. I explain why. Okay, so now what I'm doing is to explain the combinatorics, which is behind these formulas. And we will see that we will see non-crossing partitions and something which is some objects which are called Schroeder trees, which are actually in bijection with the faces of the associated. So let me explain all that. So first, non-crossing partitions. So I imagine most of you have heard of non-crossing partitions, so I will not talk too much about that. So we have a set partition of this set 1, 2, etc. n, and we draw the numbers from 1 to n on a cycle, on a circle like that, and we say that the partition is non-crossing if when we draw the polygons corresponding to the parts of the partition is non-crossing, the polygons do not cross. Okay, so here is an example with a small partition, pi 1, 3, 4 is one part, 5, 6 is another part, and we have 3 singletons, 2, 7, and 8. So the number of non-crossing partition is, of course, well known given by the Catalan numbers. And a very useful thing to consider is the so-called Crevera's complement, which is obtained in the following way. Suppose you have your partition, which is written in drawn here in black, and I insert red vertices between the black vertices, which I call 1 prime, 2 prime, 3 prime, etc. And now I try to draw the largest possible partition, with the largest possible polygons, which does not cross the original partition. I get a new partition which is non-crossing. I draw the largest non-crossing partition, of course. And this non-crossing partition is here, in my case, it's 1, 5, 7, 8. It's the partition that you can see in red here. It has one part with 4 elements, 1, 5, 7, 8, one part with 2 elements, 2, 3, another part with 1 element, 4, and another part with 6 elements, 6, 1 element, 6. So it's called the Crevera's complement. It plays a very important role in free cumulants. So now let me come to free cumulants, which were introduced by Roland Speicher maybe now 30 years ago, so it's quite a long time. The setting is the setting of non-commutative probability, free probability. We have a unital algebra and a linear form from this algebra to the complex numbers, such that phi of 1 is equal to 1. And now the free cumulants is a family of multilinear form, kappa n. Kappa n is an n-linear form, and they are defined implicitly in the following way, by this formula. So I look at the linear form phi evaluated on a product, a1, a2, an, and I say that this is equal to the sum of all non-crossing partition of the set 1n of some expression, kappa, indexed by non-crossing partition, evaluated on a1, a2, an. And kappa evaluated on the non-crossing partition is just given by a simple formula. For a non-crossing partition pi, kappa pi of a1, an is the product of all the parts of the partition pi of kappa indexed by the side of the part, P, of AI1, AI2, AIP, where I1, I2, IP are just the elements of the part pi of the P of the partition pi. Okay, and this formula defines completely the kappa n in an implicit way, and it can be inverted by using the Möbius function on the non-crossing partitions, on the lattice of non-crossing partitions. I didn't say it, but the natural order on the non-crossing partition is a lattice order, and there is a Möbius function on this lattice order, which is given by a simple formula. So the inversion formula for which gives the free cumulants in terms of the phi is given by this formula. Kappa n of A1 AN is analogously a sum of all non-crossing partition of n of phi pi of A1 AN. So here phi pi is given by a similar formula to the one that I had above, but using phi instead of kappa. And there is this Möbius function, which is here. This Möbius function is the product over all the parts of the Creveras complement of the permutation of the partition pi of -1 to the length of the part pi times the Catalan number of the part pi -1. Okay, so there is a very nice formula for this Möbius function, which was derived by Roland Speicher, but when he found this explicit formula for the free cumulants. Okay, so this is of course well known and well studied by you can read a lot of that if you don't know in the book by Nika and Speicher, for example, on the combinatorics of free probability. Okay, now I come to Schroeder trees. Okay, Schroeder trees are plain rooted trees such that each internal vertex has at least 2 descendants. So let me give some examples. Here are all the Schroeder trees with 4 leaves. So in these, so you see trees with 4 leaves. The leaves are in white here. The root is a square, a black square, and the internal vertices are black dots here. So on the upper row, I show all the binary trees. Binary trees are plain binary trees here. The plain binary trees are Schroeder trees because each vertex has at least 2 descendants. Internal vertex, of course, are vertex which are not leaves. So each of them has at least 2 descendants. And you can get all the other Schroeder trees from these binary trees in the following way. Take a binary tree and look at all the internal edges. So an internal edge is an edge which relates 2 internal vertices. And look at the left vertex edges, internal edges. And what you do is you contract some of these edges. Okay, so for example, this upper left binary tree has 2 internal vertices, edges. So there are 4 ways of either contracting or non-contracting these 2 edges, and they give me 4 Schroeder trees, which are depicted just below it on this column. So here, of course, you just contract the upper edge. Here you contract the edge which is below, and here you contract both edges. The next 3 binary trees are exactly one left edge, so there is one way to contract them. And this binary tree has no left edge. And so in this way, you can obtain all possible Schroeder trees with 4 leaves, and there are 11 of them. Okay?
Sorry.
Yes?
There was a question in the chat, namely that the root also, there was a question in the chat.
Yes.
That the root also counts as an internal vertex.
Oh, yes, it is also an internal vertex, yes. Yes, but yes, the internal vertices are the root or the the other vertices which are not leaves. Yes, internal vertices are leaves, vertices which are not leaves.
There's also a follow-up question by Dominique. He says, yes, but the tail below the, which is not drawn here, is not an internal edge. Am I right?
The what?
The tail below the root. Maybe Dominique, you want to ask the question?
Oh, the tail below the root. Oh, no, I don't, I forget about, there is no, I'm looking at, there is a root, there is nothing below the root, and I'm just looking at, well, okay, you could represent the Schroeder trees in, there is several representation. I'm just sticking to this representation when there is no tail below the root. Okay. But okay, you could put a tail if you want, but it's not useful for what I'm doing. So it's well known that these trees are counted in terms of the number of leaves by the small Schroeder numbers. These numbers are counted, of course, they are well known. You can find them in the Sloan Encyclopedia, and the generating series is given by a simple formula, simple quadratic formula. Okay. There is a connection with the associaedra also. Schroeder trees correspond to dissection of polygons. So here I put a Schroeder tree with 7 leaves, and it corresponds to dissection of a polygon with 8 vertices or 8 edges. A dissection is just a collection given by a collection of diagonals which do not intersect inside the polygon like that. So here, for example, you have 4 internal regions which correspond to the internal vertices, and you have 7 leaves which correspond to the 7 edges of the polygon which are not on the base, which do not correspond to the base. Of course, you could put another leaf here if you want to cross this last edge, but I will not do it. Okay, so it's well known that all these dissections they correspond to the faces of the associaedron. So there is a bijection between Schroeder trees and faces of the associaedron. So in some sense, everything that I'm going to do now, you could do it in terms of the associaedron. But I mean, it's since it's equivalent, I will use a Schroeder tree because it will be slightly easier to explain what I'm going to explain. But I mean, of course, you could have a completely equivalent description of what I'm going to say in terms of this associaedron. Okay, there is a kind of Schroeder tree which are interesting for us, which are the prime Schroeder trees. A Schroeder tree is called prime if the rightmost edge of its root is a leaf, and they are counted by the large Schroeder numbers, which are big Sn, and they are in fact equal to 2 Sn-1, so twice the number of Schroeder trees with n-1 leaves. So let me explain this very simply. So suppose you have a Schroeder tree T, and which has n-1 leaves. From this tree, we can build 2 prime Schroeder trees, T1 and T2, in the following way. So T1 is obtained from tree by just adding to T directly on the root, putting a leaf on the root to the right. Okay, so we see that this tree is a prime Schroeder tree. This rightmost edge of its root is a leaf. Okay, and there is another way, which is to put T on a just to uncontract, if you want, some left edge here. So this T2, the root has only 2 descendants. One of them on the right is a leaf, and the other descendant is the root of the tree T. Okay, and it's very easy to see that every prime Schroeder tree is obtained in exactly one way, either as T1 or T2 in this way, from some Schroeder tree with a smaller number of leaves. Okay, so So my interest will be in prime Schroeder trees, which are counted by simple numbers, as you can see. Okay, so now I come to some important concept, the concept of corner. A corner is an angle between a pair of consecutive edges. So suppose you make a contour exploration of your tree starting from the left. And now when you arrive at a corner, so a corner, for example, this corner 1 here, is obtained by the angle which is between two consecutive edges. So this is the first corner. Then I go again and I find another corner 2, and then 3, and then 4, 5, 6, 7, etc. Okay, so I think it's not too difficult to understand what is a corner on this picture, and I enumerate them from left to right. Okay. There is now an interesting connection between Schroeder trees and non-crossing partitions, which is the following. A Schroeder tree determines a non-crossing partition of the corners. The partition is obtained by looking at all corners which correspond to the same internal vertex. Okay. For example, here, 1 and 3, they correspond to the same vertex here. 4, 5, 6, and 11, they correspond to the same vertex. And 8 and 10 correspond to the same vertex of the Schroeder tree. And you see that 2, 7, 9, they correspond to just one vertex of the Schroeder tree. Okay, so this Schroeder tree determines the following non-crossing partitions, pi of t. Okay, now I come to a very interesting construction, which was described by some years ago by Joshua Vergès, Menus, Novelli, and Thibon, which tells you how prime Schroeder trees, in fact, encode the Möbius function on the set of non-crossing partitions. So for this, what you do is you take a prime Schroeder tree, and what you do is you remove for each of the internal vertices the internal edges which point out of this vertex, except the leftmost one and the rightmost one. So you have a Schroeder tree. The Schroeder tree is not a binary tree, and you want to convert it in some sense in a binary tree by just taking out some of the edges which are too much in some sense. So all the ones which are not the leftmost one or the rightmost one, the edges coming out of the internal vertices. So in my case, I remove this edge here, this edge, this edge, this edge, and this edge. So here I have just removed 5 edges, which are the one in red. And what does remain? What remains is a set of binary trees, actually a forest of binary trees. These binary trees are rooted, as you can see. And these binary trees, they form a non-crossing partition of the leaves. If you enumerate the leaf from left to right, you see that you get a non-crossing partition of the leaves. Okay, so this is a forest of binary trees, as I said, and it gives you a non-crossing partition of the leaves. And if you think about it, you will see that this non-crossing partition is exactly the Creveras complement of the partition pi of t. Well, it's not exactly the Creveras complement because you see it has 12 elements, and my original partition had only 11 elements. So what I have to do is I have to suppress the 12, which is here, the rightmost leaf. And if you remember, I had a prime Schroeder tree, so taking out the rightmost leaf doesn't actually take out any information in my prime Schroeder tree. I get exactly the same information. So what you see is that what you get by this construction is that you get a forest of binary tree. You get a non-crossing partition of the leaf, which is the Creveras complement. And moreover, if you want to count for each non-crossing partition, how many Schroeder trees, prime Schroeder trees correspond to this binary tree, to this non-crossing partition, sorry, you see that what you have to do is for each part of the Creveras complement, you have to construct a binary tree and put it in a non-crossing way above the non-crossing partition. And for this, the number of ways that you can do it is exactly the Catalan number, because it is the number of binary trees with this number of leaves. Okay, so we see that the absolute value of the Möbius function has a very simple combinatorial interpretation in terms of the prime Schroeder trees. Okay, using this map from prime Schroeder trees to non-crossing partitions, this map pi of t, we see that the number of Schroeder trees corresponding to a non-crossing partition is exactly the absolute value of the Möbius function. So this has allowed to these authors to give another proof of the inversion formula for the free cumulants using combinatorics of Schroeder trees. And there is some quite deep connection with the non-commutative version of the Lagrange inversion formula. So it's quite interesting to have this. And we will see that this will play a very important role in my formula here. So now I come to the formula for the loop polynomials. So what is this formula? What you do is we take, in order to explain the formula, we'll do the following construction. I take a prime Schroeder tree, T, with n+1 leaves, and a number k in 1n, and sigma a circular permutation. And what I do is that I label the corners of T by the numbers sigma of k, sigma 2 of k, etc., sigma n-1 of k, and then k. K will be on the last corner on the right. Okay, so I give you an example with my previous tree. I take the following cycle. So you see 2, 4, 8, 5, 9, 1, 6, 11, 10, 3, and 7. And here k is equal to 7. But of course, I could have just taken another number to put on the right. But here I do this. And now for each internal vertex, I call I of v the smallest label of all the corners of the vertex v. So, for example, in my and I take this expression x to be a product of the minus x I of v. So, for example, in my case, I have 6 internal vertices, and for the first one, I get a coefficient minus x2. Because 2 is smaller than 8. For this one, I got a coefficient minus x4. For this one, I get a coefficient minus x1. Here, minus x6. Here, minus x10. Here, minus x3. And I get this monomial, which is here, xt7 sigma, which is equal to this. Okay? And now, the theorem is that the generating function of these monomials is equal to the loop polynomial q sigma of x1 xn is or up to a sign is equal to minus the sum over all prime Schroeder tree of x t k sigma. And the important point is that on the left, this thing does not depend on k, and on the right, you see, so the formula on the right doesn't depend on k, which is not obvious from the definition, which turns out to be true. And so the proof of the main formula, I will not give details of the proof because it would be a bit too involved, but I will give the main ideas. So the first thing to check is that the right-hand side doesn't depend on k. For this, what we do is we rewrite the right-hand side as the sum over non-crossing partitions. It turns out that maybe I should come back. This term, which is here, x, t, k, sigma, as you can see, it depends only on the non-crossing partition, which is induced by the Schroeder tree. So you can rewrite this as a sum of the non-crossing partitions. And in this way, you can see that it does not depend on k because because the Möbius function on non-crossing partition is something which is invariant by circular permutation. This is something which is not obvious, but which is true. And it's not obvious from the start, but if you know non-crossing partition, it's not very difficult to see. But it's something which is quite subtle about this. Okay, so the first thing is we see is that it does not depend on K. So now we have to check the boundary condition. So we have to see that x1 is a factor of q sigma, and also 1 minus xn is a factor. So the first thing is easy to see because since 1 is always the smallest element in its corner, the corner 1 is always the smallest element in its x1 will always be a factor in the formula on the right. And also by the same kind of argument, you can prove you can put n at the right on your formula on your tree at the right corner, and then you see that because there is this there are two ways to build a prime Schroeder tree from a Schroeder tree. You can see easily that one of them will give you a coefficient 1 and the other will give you a coefficient minus xn. And okay, so this is quite easy to check. Okay, the continuity and the exchange conditions, well, you can look at them and you can check them. They are not too difficult to check, but this uses some simple property of Schroeder trees. But I mean, well, I mean, I will just give you an idea of what is involved in the most subtle things that you have to check. The proof of the exchange condition is obtained by doing some interesting operation on the prime Schroeder trees, which is which I call cutting a prime Schroeder trees into two prime Schroeder trees. So suppose you have a prime Schroeder tree like that, and suppose that on the right, the corner is labeled by I plus 1, and one of these corners, I here, is labeled by I here. What I can do is I can cut this prime Schroeder tree into two prime Schroeder trees here on the left, with I plus 1 on the right, and here I on the right here. Okay, I cut it into two, and this I plus 1 I put on the left, and this I put on the right. And this corresponds, if you remember, exactly what I did when I was taking a permutation, a cyclic permutation, and multiplying on the left by a simple transposition I plus 1. When I do that, I cut the permutation, the cyclic permutation into two cycles. And there is a corresponding operation on prime Schroeder trees, which correspond to here, taking this edge here and cutting the edge into two parts. One of the left will give you the rightmost leaf of the prime Schroeder tree, and one on the left, which is here. Okay, so this is this construction comes in order. Once you have understood this construction, it's not too difficult to prove the exchange condition that I had in the definition of my in the definition of the loop polynomials, in the characterization of the loop polynomials. Okay, now let me explain why the loop polynomials are free cumulants. So there are free cumulants of very simple random variables. So let me look at the interval 0, 1, including in the real numbers. And let me look at this interval 0, 1 with the Lebesgue measure. So for xx in the interval 0, 1, let me look at the indicator function of the interval 0x. Let me call it pi x. So the pi x are very simple random variables. Each of them has a very simple distribution. It takes only two variables, two values, 1 or 0. 1 with probability x, and 0 with probability 1 minus x. And moreover, they commute, of course. And the product of two of them is just the pi of x, pi y is just pi indexed by the minimum of x and y. So it's a very, very simple family of commutative random variables. And now the theorem is that q sigma of x1, xn, so the the loop polynomials that occur in the quantum symmetric simple exclusion process are actually free cumulants, the free cumulants of xi1, xi sigma of 1, xi sigma 2 of 1, etc., x sigma n minus 1 of pi x sigma n minus 1 of 1. Okay, so we have this very simple formula for Q in terms of free cumulants of this family of random variables. So it's and the proof is really just going through looking at the formula and the connection that I explained between Schroeder trees and non-crossing partitions. So it once you have seen all this, it's very simple to check this formula. Okay, and of course you just need to use this formula that the product of two of these variables is equal to pi indexed by the minimum. In particular, the expectation of the product is the minimum of the expectation of all the variables. So this explains why I had to take the minimum of the corners in my Schroeder trees. Okay, so there is a quite a simple way to see that once you have the formula for Q sigma, you can see quite easily that these are actually free cumulants. Okay, so let me summarize what I did. So I started from the quantum symmetric simple exclusion process, and I constructed a random collection matrix, Gij. So this is a random matrix of size n, which is given by looking at the correlation between what happens at site I and at site j between in my exclusion process. Okay, and now the cumulants of the entries of this matrix, they give loop polynomials as limits when s goes to infinity, and the sites at which I look at the correlations, they converge to some numbers x1, xk in the interval 0, 1. Okay, so really these loop polynomials are limits of classical cumulants of random variables. And these classical cumulants are really classical cumulants of the entries of a random matrix. So really, this looks very familiar because we have classical cumulants. This happens sometimes in your random matrix theory. You have classical cumulants, and these classical cumulants converge to free cumulants when the size of the matrices goes to infinity. But this is a very, very different situation from the usual matrix models that we consider in random matrix theory. And here we are taking free cumulants of a commutative family of random variables. So it seems, at first, it seems stupid to take free cumulants of commuting random variables because it doesn't mean anything. When free cumulants are useful when they are, essentially free cumulants are useful when they are 0, at least when mixed free cumulants are 0, because then we know that the random variables are free. This is essentially why they were introduced to check whether families of random variables are free or not. So here we see that free cumulants really can be very useful for understanding something completely different, which is a fluctuation of variables coming from exclusion process, quantum exclusion processes. Okay, so this is something which I really do not understand, except from the fact that I can do the computation and I can check from the computation that these polynomials are free cumulants. I don't really have an explanation. I do not know how to relate this to more standard random matrix theory. This is really something which is, so I would be very happy if somebody could really explain this, and in terms of the classical connection, I would say, between random matrix theory and free probability. But at present, I don't know how to do that. Okay, so I thank you very much for your attention, and that's all I had to say today. Thank you.
Thank you very much for this very illustrative and a very interesting talk. And I think before we turn to the question session, let's show our our on videos and give the speaker a well-deserved round of applause. Thank you very much.